Welcome back, everyone. And now at 20 past, whichever hour you happen to be in, it's my great pleasure to introduce our second keynote speaker, Caitlin Zadowski. Caitlin originally graduated with a BA from Colorado College, then received a PhD from UC Santa Cruz, worked for some time at MSR at Apple, and is now a software engineering manager at Google, where she manages a team of software engineers and data scientists to make data-driven decisions based on Chrome usage in the wild. I just stole that off your LinkedIn page, but it sounds like it isn't a good match with what it is that you're doing. Caitlin today is going to talk about Beyond Code, new signals for static analysis.
Thank you for that introduction. Let's see. So to start off, to reiterate, I have a PhD from UC Santa Cruz, where my interests and focus was on understanding and improving software engineering. And in particular, I was really interested in program analysis and also usability, how to make program analysis work for real developers. I've been at Google for about 8 years, though. And although I started at Google working on static analysis, I am most well known for the creation of the Tricorder program analysis platform that I'm going to talk a lot more about in this talk. I've also worked on a variety of developer tools teams there, including our code review tool, Critique, our internal code search and browsing tool. And then I helped found a new team focused on studying software engineer productivity. And in fact, I have edited a book called Rethinking Productivity in Software Engineering. So if you have questions about engineer productivity, I'm also happy to talk about that. And I currently manage the Chrome data team. So this is a team that owns in the wild metrics for infrastructure for collecting in the wild metrics about Chrome browser users, and also data scientists and product analysts that analyze those metrics and get insights about users. And we are actually one of the customers of the Tricorder program analysis platform, which I will talk about nearer to the end of my talk. So I'm going to talk specifically about static analysis, and I wanted to refresh the definition, analyzing source code. And really, I'm going to talk about to find potential issues like bugs, antipatterns, inefficiencies, etc. So problems in code, although you can use static analysis for other purposes. And the key distinction is that you can diagnose these problems without executing the program. But what else could we execute? So in this talk, I'm going to begin by giving a little backstory of static analysis at Google. Then I'm going to go into some specific lessons that we learned that we think are really useful for anyone trying to apply static analysis at a large organization or even a small organization. And I'm going to talk a little about our static analysis infrastructure, the infrastructure including Tricorder that is used daily by most Google engineers, so really a lot of engineers all the time for a lot of code. And then I'm going to talk about something I haven't talked too much about before, which is the kinds of analyzers we ended up with. But before I get into that, I need to confess something. Most of my favorite analyzers are not very sophisticated. So I know when people talk about static analysis, they often think about kind of fancy things where you have a mathematical model of different things going on in your program and you can make a provably correct statement about something happening in the program. But really, like a lot of the analyses that Tricorder has or that I've been involved in are very simple. So pattern-based, intra-procedural, inside one procedure, and just used by general developers in Google's main code base. I'm not going to be talking about verification in this talk, and the software that we are applying static analysis to is not aerospace, medical device software. But I would like to mention that some of the considerations that go into making static analysis work in this general developer's case are also important for verification as well. All right, so 6 years ago, there was a go-to fail bug, which I like because of the title in particular in SSL encryption at Apple. And essentially, there is a duplicate go-to-fail statement. And so everything after the second go-to-fail is unreachable. And this is trivially detectable by any number of unreachable or dead code detectors. But yet, none of those were applied, and the vulnerability got through. So developers didn't use static analysis tools. Why not? Even before then, at Google, there was a 2 to 3 engineer team called BugBot. And the goal of this team was to apply pattern-based find bugs. This is a Java static analysis, and also other commercial static analyses to Google's code base, I think for both C++ and Java, which are 2 of the biggest languages in terms of amount of code written at Google. And the expectation is, okay, we'll apply these static analysis tools, we'll find bugs, we'll fix them, engineers will be really happy, everything will be great. And this didn't work either. All right, so I've talked about a couple times where trying to apply static analysis didn't work out how one might have thought. So let's get into the backstory. All right, so this talk is really focused on static analysis at Google. So I need to introduce a little bit about the developer workflow of most Google developers. So for most developers at Google, we work in a monolithic repository that is more than 2 billion lines of code. And that statistic was published in 2015. So I do not have an up-to-date number for the size of the code base, but I can tell you that it has not shrunk since 2015. It has increased. We use a unified distributed build system called Blaze. This is similar to the open source Bazel. And code review and testing are just standard. So basically all code that gets written at Google, it goes through code review. And one of the things that people check for in code review is adequate test coverage. However, there's no standard IDE. So people can choose which IDE to use. There is a popular internal web-based IDE that's built on top of our own custom version control system and our own custom build system and our own custom code review tool. So that's why it's not externalized. And then also people use Vim and Emacs and IntelliJ and various other options. And for most code at Google, frequent releases are the norm. So we are developing server code where it's relatively easy to push a fix because you can just release a new version of the server. You don't have to fiddle around with distributing updates to devices, for example. And every workday, there are about 50,000 code reviews that go through the code review system and the accompanying analysis infrastructure. And some of these are actually generated by robots and some of them by people. So in this environment, to make static analysis work, there's kind of 2 key things that sound simple, but actually encapsulates a whole lot of difficulty. So the first is scalability and the second is usability. So when I tell people kind of like what it took to make static analysis work at Google, it was really scalability and usability. All right, so what do I mean by scalability? So first of all, modern software is much larger than it used to be. So the Tricorder prototype, so kind of like getting Tricorder working initially on sort of first thing that we could show people, like here's something to build off of, let's see if we should staff this further. The prototype had to work on programs that were hundreds of millions of lines of code. And it had to work for tens of thousands of software engineers and tens of thousands of code reviews a day. And the other thing I want to mention about scalability is there's a few different dimensions of scalability to consider. So first, like the analyses that you're writing have to scale. So like Tricorder had to scale. It had to be able to run on so many code reviews all the time and show results to all these people. But also, and to do that, we had shardable, incremental or compositional analyses. So that's kind of the techniques that people employ to make the analysis platform or analysis scale. But there's also scalability in terms of making more analyzers to run over the code base. So allowing the contributions to scale. So you don't have a bottleneck where just a couple people are writing all of the analyses. And then another side for scaling is in terms of the process. So you want to show these results to people. You don't want to have a bottleneck where you're only showing them to a subset of people. And so like Tricorder hooks into this process via code review. The other key thing to make static analysis work is usability. So there is a cost-benefit trade-off when considering analysis results. So the benefit is that you can prevent, for example, a bug from entering the code base or an issue from occurring. But if you change code that's running fine, you could actually introduce a bug while fixing one, for example. There's a cost in terms of developer time if people have to look at the code review analysis results or anywhere that you show analysis results and consider whether they want to make a change to the code base. So when you think about how to increase the uptake of static analysis, you could increase the benefit, make it really clear that some analyses are really useful, but you can also think about decreasing the cost. So this is things like automated fixes, like can you make it just like one click to apply a fix that removes the problem? Also reducing false positives, so you have less time kind of trying to decide if a analysis warning is a real issue or not. And also making the workflow integration really smooth so people don't have to switch contexts, for example. All right, so let's go back to the BugBot team. That did not work out super well. So the first version of BugBot involved nightly runs over the whole code base, bug reports stored in a central database, and you could make a query to find out what kind of bugs were in this database for your project. However, people did not really use this database. It was outside the normal workflow. You had to make a query to something special, and engineers just didn't want to go out of their way to visit this. The second attempt was the BugBot team manually triaging new bugs from nightly runs. So this at least dealt with the problem of making sure that we were only highlighting kind of things that people really should fix. So they filed bug reports for the true positives, and they fixed even things that they could manually. But it became clear that this was just too labor intensive, and it wouldn't really scale well as the code base kept growing and growing. So the third integration was in code review, just like Tricorder eventually did. And BugBot was running over the find bugs over patches sent for review, and warnings were shown as comments. And this is in the previous code review tool before critique. However, users could suppress false positives and users could filter by confidence. The fact that there were false positives at all really made developers lose trust in the whole tool. And also old issues, so issues that had previously been in the code, but that were surfaced during the review were distracting. So I've mentioned the word false positives or the phrase false positives a couple times. So I want to dig into that a little bit. So with Tricorder, when we talk about false positives, we talk about something we like to call effective false positives. The key thing here is that the perception of a false positive matters. So if a developer views the result as a false positive, that's kind of really what we care about. So for example, it could be a true positive. So like your analyzer could be actually correctly highlighting a problem in the code. But if the message is too confusing for developers to actually understand what's going on or make the fix, then we still consider it an effective false positive. If it's, again, like technically correct, but it's just not important, so people don't want to make the fix, then again, it's an effective false positive. So the effective false positive rate is the sort of user perceived false positive rate by the tool. And because it's a user perceived thing, we can't really measure it exactly. So we have to measure it by proxy. You could estimate it with the fix rates, or you could also do what we do, which is actually ask people whether results are useful or not. All right, so to summarize, developers consider the cost-benefit trade-off when thinking about static analysis results. It is challenging to get developers to go out of their way to use a separate static analysis tool. And also results may be ignored when they're not actionable or understandable. I mentioned briefly, like user-based configuration is problematic because you don't get a consistent view. I'll talk more about that in a little bit. And you don't want to keep surfacing old bugs. Fixing a bug is a risky thing for code that is not changing often because you could introduce a new problem, for example. And false positives really make developers lose trust. And trust is something that, in addition to it being bad to lose trust, when you have gained trust, you can capitalize on that and take advantage of it. All right. So that's kind of the backstory of how we, this kind of state of things before the tricorder analysis infrastructure. I'm going to talk a little bit about the lessons that we learned. So I have kind of given a talk like this or had a conversation like this several times, and I've formulated the lessons a few different ways, but this is the formulation that I like the best right now. So distilling it into 3 things. So focus on developer happiness. Make static analysis a part of the core developer workflow, and empower users to contribute. So what do I mean by those? So when you really want developers to use the analysis tools, the developers are your customers. You need to track the performance of the tool and actively solicit and act on feedback, so that you can really get into this virtuous cycle with developers where they tell you problems, you fix problems, you build trust, and then improve the tools at the same time. And really like focus on users feeling like they benefit from the tools that you're creating. Second, making static analysis a part of the core developer workflow. So this is going back to this cost-benefit trade-off where like making smooth workflow integration really reduces the cost for people to look at and apply static analysis results. So for Tricorder, the integration point that we've used is code review. And code review at Google, as I mentioned, is this sort of nice gateway because all change goes through review, but actually there are several benefits to surfacing analysis results in code review. For one thing, developers are in a change mindset. So you've written some code, you're sending out for review, you're kind of expecting feedback at that point, and you're expecting to change the code that you've written based on feedback. So if an analysis tool gives you feedback, that's the perfect point. It's also similarly a context switch point. So when we look at patterns of developer behaviors, we see that after sending code for review, developers will switch to a different task for a little while. So you have several minutes for analysis results to complete, or even longer. Another nice benefit of code review specifically is there is a peer pressure aspect, where if you show results in the review tool, the reviewer, in addition to the author, sees the analysis results. And if the author does not fix something based on an analyzer, the reviewer can say, why haven't you fixed this? Can you explain to me what's going on? And there's also this, it makes the benefits more clear in terms of saved reviewer time. It can also make it easier just to have some of the kinds of discussions you have in review by having an analyzer surface a problem instead of having the reviewer need to surface that issue. And lastly, empower users to contribute. So with Tricorder, we built a program analysis ecosystem. And the key thing here that I want to emphasize is there's not really enough analysis experts. And also, analysis experts are not necessarily domain experts. So at Google, we have a lot of people that are experts in a particular API or a language or some kind of configuration technique. And by allowing them to contribute, you've really expanded the space of possible analyses that you have. And also, the other thing I want to mention is that a lot of engineers really love this kind of work. And also it can be very satisfying to, for example, encounter a bug, get really frustrated at the bug, and then realize that you can introduce a static analysis check so that no one else will have to deal with that bug again and not know how to deal with it. So by making it easy for developers, across the company to contribute, we've really expanded which analyzers we can show. All right, so I'm going to talk a little bit about Tricorder now. So Tricorder, there's a 2014 paper, and also it's discussed a lot in a 2018 CSM article if you want some more reference. It is a static analysis platform that you can plug in different analyzers and show the results in code review. And the analyzers can be written in basically any of the top languages at Google, which is Java, C++, Go, Python, and JavaScript. Tricorder is based on a microservices architecture. So you send an analyze request whenever there's a new kind of code review patch ready to analysis services, along with metadata about the code change. And those analysis services run a variety of analyzers, and they use a fuse-based file system to read the files in the change, and both in the before and after the patch. And Tricorder also takes advantage of our distributed build system and the fact that we have cached build inputs and outputs that the analyzers can build off of. And Tricorder also uses, as I mentioned, feedback channels to get feedback from developers while in the review and send that back to the people that actually wrote the analyzers. And the sort of key design points in Tricorders is focusing on value to users. So making, once we had the prototype working on those, 100 million lines programs, how do we make sure that it's really useful? So this is an example of what a Tricorder warning looks like in Critique's diff view. So Critique is a code review tool. So Tricorder produces these like gray boxes. So the top one, it just says you're missing a Javadoc comment. It's a lint error. And you can click on the left, please fix, or on the right, not useful. And the next one, string comparison using reference equality instead of value equality. This is an error-prone warning. I'll mention error-prone a little more in a minute. And if you notice, there is a suggested fix attached. And if you decide to show the fix, it pops up a diff view and you can apply it directly to the piece of code. This is the change author view where they can apply the diff. So by the numbers, there are currently more than 200 analyzers plugged into Tricorder. And at least 7 of those analyzers are themselves plugin systems where you have many other analyzers that plug in. There's more than 30 languages that Tricorder analyzes. And also Tricorder supports analyzers written in 5 languages kind of natively, and then others if you call it to a sub-process, for example. People apply 3,000 automated fixes every workday. And in addition to, this is just the automated fixes being applied. In addition, like people click on please fix, I think 5,000 times every workday. These statistics are from, I think 2018, published in 2020. And Tricorder analyzes more than 50,000 code reviews every workday. All right, so going back to the feedback channels, analysis results have not useful and please fix buttons. These are used by reviewers mostly, although not useful, the change authors can also click on. And the Tricorder team tracks the ratio of not useful and please fix clicks. So essentially, if there's too many not useful clicks relative to fixes being applied or people clicking on please fix, like if that ratio gets too high, then the Tricorder team disables an analyzer. The other key thing that makes this work is, this is kind of an implementation detail, but it ended up being really important. When you click not useful, it invites the user to file a bug against the analyzer author. So we've managed to kind of take the platform out of the feedback loop in order to give the analyzer author feedback directly and quickly. And then analyzer authors will change analyses based on bug reports. And we have some great examples where, for example, people were clicking on not useful a whole bunch, and then it turns out that it was just the error message that people were confused by. And when we fix the error message, that rate goes down. And remember, like, if the error message is confusing, that's still an effective false positive. And so that's still a problem that you need to fix, just as bad as if the analyzer is producing a result erroneously. I just want to briefly touch on, this is kind of from 2015, so it's from a little while ago. This is one of the first C++ analyzers that we integrated into Tricorder. So it's the number of the y-axis shows the number of instances of this problem in the code base. And this is a redundant smart pointer get call in C++. And the x-axis shows time, and the vertical line is when the check was to find this was introduced in Tricorder. So as you can see, we sort of steadily had an increase in the number of instances in the code base. And then once we introduced the check in Tricorder, instead of kind of leveling off, we see actually a drop. So people began fixing this problem in other places in their codes. This was kind of the first evidence that people were really learning from Tricorder analyzers and becoming better programmers because of it. Another thing that I wanted to touch on briefly is per project customization. So I mentioned, like, way back in the beginning of the talk, when we were talking about BugBot team, how you could have a per user customization and hide false positives that way. And this didn't really work out. So user customization is often problematic for a variety of reasons. First of all, it gives a discrepancy between the view of the code base that a particular team has, or even like across teams. But one thing that we've seen is one person on a team will be sort of like fixing all instances of a problem, and other people on the team will actually have hidden that from their view through user customization, and they'll be like actively like introducing new problems. And that's not a great place for the team to be in, either just like in terms of team dynamics or in terms of the code base. Also, when users hide false positives, you don't find out about the false positives, so you can't fix the problem. So for example, when we first disabled user customization, we had some kind of simple like lints, like mostly style checks enabled, and previously people could suppress false positives, and we stopped allowing people to do that. And all of a sudden we got a lot of bugs filed. It's like, there's all these problems, like, fix the issue. One of the things we discovered was that the C++ linter was running on Objective-C files and linting them very poorly. But basically everyone that worked in Objective-C just like went to the settings and turned off lint in all their code, and then didn't see any like style suggestions anywhere. And then it wasn't until we disabled that option that we discovered this. We were able to get the C++ linter to stop running on Objective-C files and in fact add an Objective-C linter. Also, you want to make sure that a warning is kind of like seen by everyone. They have a consistent view of the system. So Tricorder allows per project customization. Most analyzers are on by default, but you can additionally add extra optional analyzers. So we still have sort of a base like view that everyone at Google shares, and then this extra stuff on top of that. One thing that's kind of nice is analyzers now have the ability to start optional and then kind of graduate to on by default after you get to a point with like iterative feedback and trust built. So one example there is we had an analyzer that is showing problems in Java code, Java optional suggestions, but they're not correctness typically. They're more kind of readability, like this code would look cleaner if you made this change, this equivalent statement. And at first we thought developers would be annoyed by having this on because it's not a bug necessarily. But kind of over time, after enabling it as an optional analyzer, after iterating with feedback, like we were able to turn it on for everyone, and developers actually liked it. There's also a project called Tricium, which is Tricorder for Chromium, which is an open source version of the Tricorder platform that plugs into the Garrett, which is again an open source code review tool. And you can create and deploy analyzer packages, and it leverages Chromium's distributed build system, Lucy, which is also used by a few different projects. So it's another thing you may want to check out. Actually, on my current team, we use Tricium to analyze new metrics that people add to Chromium. Okay, so in addition, so it's kind of Tricorder is, a big thing that I worked on at Google, but there's also other integration points for static analysis. So, for example, during code editing, that's also a nice point where people are in a change mindset, in that they are actually actively working on a change. However, analyzers in code editing, like ideally should be very fast, so they don't interfere with the sort of like read, modify, edit loop. They also need to be IDE independent to really be used consistently. One thing I do want to mention is that we have moved to a formatting model where for just kind of like stylistic changes like spacing and things like that, you can just kind of automatically format your code so you don't have a whole bunch of small comments to deal with or apply. Also during compilation, is another place you can surface analysis results. I mentioned Tricorder is surfaced during code review. We also have pre-submit, so basically something where you can check something before code is committed and kind of guarantee that this analysis runs or passes before you're allowed to commit something. Although I mentioned that showing results in code browsing is not always useful because it's not kind of part of this workflow necessarily for developers. In some contexts, it is really useful. So for security issues, for example, you may have a separate security team that's reviewing all the problems, or if you are planning a cleanup and you want to see how often a problem occurs in the code base. So compile time checking must be faster than code review checking. And one thing I do want to mention is that we don't have we've moved away from compiler warnings. We do have them in some cases, but we're moving away from them. So really just break the build. We found people ignore compiler warnings. So when we add a new static analysis to the compiler, we want it to be something that we can break the build. So ideally it's a correctness issue. It has, basically no effective false positives. And also it has to be easy to fix, because what we do is we actually remove all the existing instances in the code base. So when you have a new compile time check, you first enable it in Tricorder. So this prevents backsliding, for example. You run the compiler over the entire code base, which takes about 20 minutes. Collect diffs from the suggested fixes, create a big patch, and send that out using Rosie, which is something that takes a large change for large scale changes and distributes it across the specific people that need to review it. The other thing I want to mention briefly before getting into analyzers is that there are other analysis teams at Google that are working on program analysis tools that have other flows and kind of other specific problems they're solving. So there is a 2019 FSE paper about Fudge, which is a fuzzing-based test generation tool for Google Scale. So this to speed up the process of adapting fuzzing, this tool extracts library usage patterns from clients, and we have this big code base, so a lot of library usage patterns, and turns them into fuzz targets. And then there is an automated evaluation process to go through those targets and suggest like some likely useful tests. And then humans get involved to actually vet cleanup candidates and check them into the repository. Another example of a way we're applying analyses kind of outside of this like Tricorder system. or Tricorder workflow is Deep Dive, which is security analysis for Android apps. So this is a framework for detecting vulnerabilities and malware in Android apps that's so far been involved in fixing more than 80,000 Android apps. So this is taking APKs and data from the Play Store, doing the analysis, leveraging machine learning, and then producing malware reports and vulnerability reports. And in this case, we're analyzing apps that we don't necessarily own. And so it's really like security reviewers that are involved in deciding what to do with the results. Okay, so let me talk a little bit about some of the analyzers that have sprung up since we created Tricorder. So before I get too far into this, remember my confession. Most of my favorite analyzers are not very sophisticated. They are typically simple analyzers, so pattern-based, interprocedural, and they're used by general developers in Google's main code base. However, I think there's a lot of interesting ideas here, and I think that sort of considering from the sort of program analysis academic side and some of this sort of real world, practical, interesting stuff that people do with analyzers, I wonder like what we might find in that intersection. So there's a few different types that I'm going to talk about. So like finding antipatterns, thinking about the larger context, the outputs of code, and keeping the code base in sync. So when you think about antipatterns, like first I talked about error-prone a little bit earlier. So this is kind of a more traditional anti-pattern static analysis tool. So error-prone involves modifying Java-C to add an extra error checking pass over the AST. Checks are modular. They're written in a declarative matcher style. And it's really easy to incrementally add new checks. We've had contributors from all across the company. We've had interns contribute. It's an open source project. We have people from outside Google contribute. Checks provide suggested fixes that are structured as diffs, and they can be applied mechanically. For example, when we are adding a new error message to the Java compiler, we do that cleanup where we run Java-C over the entire code base with error-prone turn on with the new warning enabled. You can also present an error message when someone is compiling code or in Tricorder. However, anti-patterns are not just for code. So another analyzer that, and most of these analyzers are not analyzers. So I was involved in error-prone, but most of these analyzers are not written by me. They're contributed by kind of arbitrary developers throughout Google. So the respectful code analyzer looks for sort of anti-patterns in the language you're using. So for example, stop referring to master versus slave processes. This is terminology that is deeply offensive to many people. And so this is really a static analysis that is affecting a social change that also is like trying to make the engineers more comfortable instead of like affecting the, instead of to change the like correctness or something of the code. Another example of anti-patterns is for data, how data is stored. So at Google, we use protocol buffers extensively, which is a language neutral mechanism for serializing structured data. So if you are developing a server, that server will take protocol buffers as input and output on the RPCs it makes, for example. And there is a proto best practices analyzer, which looks at protocol buffer definitions and highlights potential issues. So for example, if something looks timey, like you are maybe creating a time field, but you don't specify the units. I mean, this is heuristic, but this is also a problem that often happens when people are specifying a proto definition. It also looks at things like potentially breaking data format changes. So for example, there are some changes that are problematic only when serialized data is stored somewhere, like in server logs. So you can enable this for your project if you know that you have that kind of situation. Another example of where anti-patterns come up pretty often is configuration. So at Google, we have many, many configuration languages and many, many contexts for configuration. So one example is a database schemalize analyzer. So database schemas can be difficult to get right. So for example, we have a few checks here, like checking that at least one admin user has read-write access, because if there is a problem with the database and you need an admin to fix it and they don't have read-write access, it's easy to not be able to deal with the issue that's come up. Another thing that this analyzer checks for is looking at potential hotspots in accessing data. So essentially, when this is a distributed database system, and if you have and the work is distributed based on the primary key, and if you have a monotonically increasing primary key, then the sort of last worker will always end up getting all the right tasks, and you'll be bottlenecked there. So there's a check to make sure that you don't have a monotonically increasing primary key. A common example of something like this you might have by accident is using a commit timestamp as your primary key. I'm going to talk a little bit about Finch experimentation configs in a bit, but that's another kind of config that we check. And lastly, I want to mention there is a Tricorder configuration analyzer that makes sure that all the enabled analyzers in Tricorder provide a place for filing bugs, and also make sure that when you enable an analyzer on by default, it's already been released to production. And the way that this analyzer does that is by sending an RPC to the Tricorder analyzer service. So analyzers can make RPCs. I think that's like one of the big benefits of a system like Tricorder is analyzers can make RPCs to a variety of places. So I'll mention just a few other examples. So we have when we import open source projects, we import them into third party, and third party, there's a code checker that checks issues with imported open source code, including that they uphold standards, like you have to have multiple owners for a open source project if you want to use it. And also it makes an RPC to a service that looks at external vulnerability feeds and tells you if there's any open security issues for the project. Another example is the missing translations analyzer. So when you are making UI changes, you have a UI string. Google is a global company, and you need to have translations to make those UI strings intelligible globally. So this analyzer generates an XML file with new and untranslated messages, and then verifies whether the entries actually have a translation. So you have an RPC to make sure the strings are actually translated. And this analyzer is configurable, so you can specify languages that you definitely need a translation for. Another example, this is kind of like a short but sweet one, is to identify broken to-dos on change lines. So you can specify to-do in code and mention someone's username. And this analyzer makes an RPC to make sure that the username actually exists, or bug ID. Another class of analyzers is looking at the outputs of code. So not looking at the running program, but looking at something at before and after the change, how big of the binary increase, how big of the size increase you have. This has ended up being important in situations where you really have to watch your size. We also, general system where you can, called the build-based config platform, where you can, for example, edit a dot file, which is a specification language for graphs, and then see the generated PNG. So you can kind of like leverage the build system to view arbitrary generated files. And another example of something you may not think about as an output is an analyzer we call on-call board. So this is analyzing the configuration for an on-call rotation. So on-call schedules are specified in a config file at Google. And when you change that file, on-call board visualizes the config changes and ensures that the rotation is balanced, so that you're not kind of accidentally increasing the number of weeks that someone is on call too much. One last category I want to mention is analyzers that work to kind of keep the code base in sync. So you're analyzing one program, but you're leveraging kind of general information from the rest of the code base. So for example, we have a deleted artifact analyzer. So if you delete a source file that's referenced in other non-code places that are also in the code base, like inside some documentation files, like basically if you reference the path to this analyzer somewhere, if the path to this file somewhere, the deleted artifact analyzer will tell you. So leveraging code search to find anywhere in the code base that the path is referenced, or potentially other places as well. We also have an analyzer that allows you to specify which portions of files need to be synced together. I know it's kind of an anti-pattern to say like you have to always modify these two files together, but sometimes it happens. For example, when you have source code and a configuration and they're both needed to run something in a production environment, and you need to keep some of them in sync with each other, you have the ability to specify that with the if this and that analyzer. All right, so kind of putting this together, I want to talk about an example of an analyzer that does all these things. And this is also an analyzer that my current team uses. So Finch is Chrome's experimentation platform. So Finch configuration files specify the size of the treatment and control group on the population of people that use Chrome, the Chrome version needed to run a particular experiment. And there are many potential gotchas with sort of specifying your experiments, like forgetting to have a control group, for example. The analyzer tool, in this case, is used by the team maintaining the Finch experimentation platform. So it's really used by the code reviewers, even more so than the code authors, kind of as a check to make sure that they're reviewing for the right things. And kind of all these examples of things the analyzers do that I mentioned, like Finch does. So it finds any patterns in experiment configuration files, like not having a control group. It sends RPCs to check that you have the appropriate leadership approvals to launch your experiment. It sends RPC to the bug tracker, which is also where we track launch permissions. It analyzes the code outputs. So the Finch config and the reviewers look through the protocol buffer, and also the analyzer is leveraging that. It is keeping Finch configs in sync with Chromium testing configurations to make the way that we're doing experimentation and the way that we test on our sort of test waterfall. And to check things like that experiment names don't clash between different experiments, so that you don't have issues when you go to look at your experimental results. And it does other things too. So like there's many other kinds of things that analyzers do, such as comparing with all the other currently running experiments to identify potential crosstalk, like when two experiments may affect the results of the other because there's too much overlap in the group assignment. So that's it. I hope you enjoyed my talk. I hope you enjoyed thinking about some of the kinds of things that static analysis tools can do that are kind of not commonly talked about, say, in the research literature. And I just want to re-emphasize the kind of 3 lessons that we learned with static analysis at Google to get developers to really use the tool. Focus on developer happiness, make static analysis a part of the core developer workflow, and empower users to contribute. And once you've done that, see what kinds of new signals that you can incorporate in your analysis tools.
Thank you very much, Caitlin, for the great talk. So we already have quite a number of questions lined up, so I think that really got people going. The first 3 questions are from the same author, so I'm going to alternate a little bit with the later questions. The first question is by Krishna Narasimhan from Technical University of Darmstadt, and he asks, how does Tricorder ensure the separation of roles between analysis expert and API expert? Or to rephrase, how much of a learning curve is it to write the extensible plugins? Is there an internal DSL?
So I guess there's an internal DSL in that there is an internal API, and an API for writing an analyzer plugin is essentially allowing a DSL, defining a DSL. You basically implement an analyzer service, and there's a service interface, and within that you get your analyzer to do stuff, and you can read the source code and read other information. I mentioned protocol buffers. There's a giant protocol buffer that includes all the metadata you might want about a change, so you can read things directly out of the change. And Google developers are often used to writing server code, so it's like writing an analyzer into writing a server. So that's easy for people. And the sort of making sure the service runs stuff is also taken care of by the Tricorder team. So you can implement the service, and then the Tricorder team will actually kind of run it as part of their larger like Java analyzer service. So you don't have to deal with the kind of annoying making sure that you have enough resources to run on some machines and which machines you run on type stuff. So I think based on the fact that we have hundreds of contributions from throughout the company, and we've even had interns who are kind of like 2nd-year undergrad interns come in and write analyzers. So I think like it's relatively easy to enable.
Okay, thank you. Then for the next question by Geoffrey Reedy from Sandia National Labs. Is there a strategy in Tricorder or otherwise to represent analysis findings that were previously rejected as perceived false positives that may now be accepted given user experience improvements in the analysis? So explanations.
So often when we see, so analyzers have, the category, so like error prone is the category, and then there's a subcategory for the particular type of like pattern of problem. So like all the specific checks in error prone are subcategories. So when we look at people clicking like the not useful button, for example, we're looking at not just the category, but also the subcategory. So then we can highlight, not just like block the analyzer, but like this part of the analyzer is the part that people are having a problem with. So I think often a common flow is to have a subcategory that's getting like a lot of people annoyed at it, and then to go, the analyzer writer, like you see like a bunch of bugs for this one subcategory, and then you kind of rethink like what that particular subcategory is doing and potentially fix the issue. So we've seen many times being able to just change the message, like not change the analyzer, but change the message, and having that completely change how the analysis result is viewed by developers. So we definitely do have that flow where like something at first we would want to block it because it's so annoying, but then we're able to refine the problem.
Okay, thank you. For these kinds of messages, do you have some general recommendations for people who work in program analysis, how to write good messages?
Yes, so I think the biggest thing I would say is to test them out with other people. So user evaluation is something that seems really scary, but really just getting someone else to use your tool that is not someone that's worked on the tool can make a really humongous difference. And it doesn't have to be that you like follow a protocol and have, you know, a sort of publishable like evaluation with enough users. Like even just having a couple developers that you know test it out and give you feedback can make a really big difference.
Thank you. Next question again by Krishna Narasimhan. If the developers are allowed to code in whatever IDE they want, do they also get IDE integrations for the extensible static analyses, or do they need to constantly shift back between command line and browser, command line or browser to use Tricorder?
So Tricorder is mostly surfacing results in code review. So then we've sort of sidestepped that whole issue of which IDE people are using.
Thank you. The next one is by Lingwe Luo, who asks, how do you handle false positives reported by the users? Do you just suppress them or actually use them to improve the analysis? On such large-scale code bases, you can have, she imagines, a machine learning-based approach to filter false positives based on user feedback. Is there such an approach?
We are not using machine learning to filter false positives. Instead, right now, we're mostly refining the analyzer. So like servicing the false positive rate to the analyzer, disabling a specific part of a check if it's problematic, and kind of like making sure the analyzer, so the Tricorder team is making sure that the analyzer actually does address issues.
Thank you. Next one by Anurag Agarwal. In the beginning, you mentioned allowing users to write their own static analysis rules. This must have some sort of learning curve for developers on how to write their own rules. Is the learning curve too steep, and how were you able to manage this learning curve?
So I mentioned that for a Tricorder check, you know, it's using this like RPC server interface that people are used to. However, there are also Tricorder checks that are plugin systems like error-prone. And there's even, people have contributed various things to make it even easier to write analyzers. So there's a system called Refaster that I think we've published about at a workshop, which allows you to specify as just Java like code snippets, like before and after code. Here's like what, you know, this statement looks like before and after, and it will take that and generate a analysis that does that transformation and finds instances of the first and replaces with the second. So I think we're able to kind of leverage a variety of different things to make it easier for people to contribute.
Thank you. Then just a quick comment from Bill Pugh, who says, nice work, glad to see all the progress. And then we have a question from Julian Dolby from IBM Research, who asks, for making analysis part of the workflow, do you see the IDE as a good place to put analysis?
Yes and no. So the issues with the IDE are this, you know, like you ideally want analysis results to be fast in an IDE. And you have this issue when you have people using different IDEs that you need some, you know, language or IDE independent way to surface results. I think an IDE is a great place to surface static analysis results, but I think there's also other things that you want to surface in code reviews, like analyzers that take longer, or analyzers where you want that peer pressure aspect, because I mean, that's one of the really powerful things that code review gives you.
Thank you. Then we have one question by Marat Akin from JetBrains Research and St. Petersburg Polytech. And he says, thanks for an awesome talk. Have you ever encountered situations where the signals proposed by the devs for inclusion in Tricorder and co were non-beneficial or wrong in some sense?
So we definitely have people enable experimental optional analyzers. So I think there's a higher bar for the on by default, but you can add something to Tricorder and then allow teams to add it to, like, in their Tricorder configuration file for their projects. And we definitely see sometimes that people will get annoyed and will rethink like whether it's a good idea or not.
Thank you. Then we have One question by Munawar Hafiz from Open Refactory. And he says, there's a difference between generating a fix and generating a fix that is human-like and can be acceptable. How complicated are the fix suggestions and how often are the suggestions accepted?
I don't know if I have off of the top of my head a statistic of like how often there's a fix suggestion versus the fix accepted. We also see people, like sometimes people will apply the fix using that flow with the apply fix button, but also sometimes people will apply the fix by incorporating it by changing the code, rewriting the code to incorporate it. I think it also depends on how narrow the problem is. So if the problem is like a portion of a line, like for example, the redundant get call on a smart pointer where the fix is just to remove the second get call and remove the .get basically, then that's something that's pretty easy to like clearly an improvement. If you get kind of more complicated problem, then it gets a lot harder to specify a fix that looks good.
Thank you. While we are technically out of time, maybe we can do 2 more minutes for 2 more questions that we just got in, if that's okay with you.
Sure.
Okay, first one is by Yoshiki Takashima from CMU, who says, it seems that there's a significant, I think, significant educational element to your project. How valuable do you think your tool will be in an educational setting?
I think potentially useful, and that's if you have specific anti-patterns you're trying to get people to avoid when writing code, you could specify them as an analysis rule. So you could imagine doing something like this for grading student programs where you look at like some, I mean, I remember from when I was a TA grading student programs, there were some problems that were just way more common than I would necessarily expect like in industry. And so you could write an analyzer that says like, whenever you're doing this kind of bad thing, like highlight it and point it out.
Thank you. Next we have Ziheng Liu from Penn State. Since developers prefer fast checkers, what should we do to deploy, test, and improve complex techniques like context-sensitive pointer analyses and model checking?
So I think you still can have slower checkers. The code review, I think that you often have about I forget the median time to the first review, but you could have analysis results in an hour and something like that. Tricorder also, one thing I didn't mention too much is Tricorder also has intermediate status updates. So you have an indication in the code review tool that an analyzer is running and results will be ready soon. So like, ways to make an analyzer faster by like caching intermediate results, for example.
Thank you. And there are a few more questions in the discussion thread, so people are really excited about this work, I think. So I'd encourage you to try going there and answering them in the break if you have the time. Otherwise, we have some 16 minutes now, I believe, for break time. And after that, we'll be back with our last session, which will be a few more tool talks, 3 tool talks, and finally the wrap up. So thank you very much again, Caitlin, for the great talk.